Good morning. In today's lecture, I want to talk about the activity series of metals and batteries. So two more topics related to redox reactions. And so the so-called activity series of metal is a ranking, if you will, of metals that list the most easily to oxidize metals at the top and harder to oxidize metals at the bottom. And so this basically allows us to figure out what metals are going to be most reactive or most susceptible to undergoing oxidation, to losing electrons. Metals at the bottom will be lower reactivity metals, and they won't want to lose their electrons nearly as easily. And so they're going to be more difficult to oxidize and less reactive. So if we take a peek at the activity series, we'll see that we list this as a series of oxidations, right? Now, if we notice, the most reactive metals that we know about, right, are group 1 and group 2. And you can see these are all listed at the very top of the activity series here, with aluminum sort of being the first metal that's not in group 1 or 2 there. So the most common, the most reactive of maybe the metals that we think about in terms of actually working with. And then we kind of go from there. We see things like zinc are really reactive, iron is pretty reactive, and then nickel, tin, lead. We start getting into these less reactive metals, and down at the bottom we have metals that have very little to almost no reactivity: copper, silver, and gold. And so again, metals at the top of this table are going to be the most reactive, most easy to oxidize, have that strong tendency to lose electrons. Ones at the bottom are going to be low reactivity, hard to oxidize, don't really want to lose their electrons. So if we look at these half reactions, right, the ones at the top, right, are more likely to occur. So the stable state, or where these metals were most comfortable or more stable, are going to be in their ion form, right? And this is, if we think about nature, most metals don't exist as pure metals in the earth, right? They exist as part of ionic compounds, as what we call ores, right? So, aluminum and zinc and iron, right? We find these as compounds in the earth, and they have to be refined, right? These iron ore, aluminum oxides, right? These things have to be processed in order to get the metal, right? Because they're more stable, or the sort of the stable form of them is the ion. Whereas some of the metals that we do find in nature, like silver and gold, we can find at least some deposits of them in their pure form, because those metals are more stable as pure metals and less likely to undergo oxidation to form those ions. Now, the other thing that we can do is we can pair an oxidation from somewhere maybe on the top part of this chart with a harder to oxidize metal that will likely go in the reverse direction. So a reduction. So these are all written as oxidations, but any of them, for example, let's say copper, could be written as a reduction. So if I were to write these, and so a lot of times if we mix the ions of these metals very low with the metals near the top, then we have a pairing of a metal that likes to be oxidized, likes to lose, paired with an ion that likes to gain. Right? And so if you pick the right pairings, you can get a what we call a spontaneous redox reaction. And that's what we can sort of look at here. Now, as I mentioned, gold, silver, platinum, which is not on the table, right? These are very low activity metals. They don't like to tarnish. They don't like to corrode. They don't oxidize, right? So these are why these metals have always been used for things like more like jewelry, coins, because they're quite stable, right? They're going to retain their luster. They're not going to corrode over time. So, using the activity series, right? So, if we take a magnesium strip, right? Something from near the top of the table, right? And we take copper, a metal that's close to the bottom of the table, right? Well, magnesium metal really wants to exist as the ions, right? So this magnesium strip, if it has someplace to give its electrons to, like ions that want to be reduced or that are easier to reduce, then we'll get this reaction to occur, right? So we have magnesium being oxidized to its ions, right? High in the activity series. We have copper ions being reduced to copper metal because it's lower in the table. So if we look back at this table for a second, we can summarize that by saying any metal will give its electrons to the ions of a metal below it in the table. And so we think about that as the electrons will flow downhill. So in this case, we have magnesium will lose these electrons and give them to the ions of some metal below it. So we'll get this oxidation to occur and the reduction of the lower one to occur. So we end up forming the magnesium ions and the copper metal. Now, these spontaneous redox reactions only occur in one direction, right? So if I try to make the opposite pair, where I try to get copper metal, right, to give its electrons to magnesium ions, right, that would require electrons to flow up the table. That will not happen. And we'll see that, we can mix these two together, but they're just going to sit and stare at each other. Nothing will actually happen. So we can use the placement of these metals in the activity series to predict if they will spontaneously react with each other, or if a reaction will occur spontaneously as written. Now, another thing that the activity series can allow us to do is to see how metals will react with acid. So again, if we look back at the activity series, we see that in amongst the metals, we have this hydrogen reduction. Right? H2 goes to H plus 2 electrons. Now this is here so that we can look at, right? This is what's going to happen in an acid, right? In an acid, these ions are going to be reduced to form hydrogen. So what that means is that any of these metals above hydrogen will easily react with acid, right? And so they will give their electrons up to the hydrogen ions that are going to be present when we have an acid solution. Remember, when we talk about acids, they generate hydrogen or hydronium ions. They're going to give their electrons to the H ions and form hydrogen gas as the product. And so these metals will all react pretty easily with acids. Now, metals that are down here will not. At least they won't react with all acids. And so we think about, again, silver, gold, copper are more resistant to reaction with all kinds of things, including acids. So most acids do dissolve metals, but not all metals. Right? They have to be metals above that hydrogen on the activity series. So it's just a matter of looking at the series and finding where it is, and you can predict it. Right? And these metals, when they react with a common acid like HCl or HBr, etc., will produce hydrogen gas. Now, nitric acid is weird. It's kind of a strange one. It has the ability to react metals below it on the table. Because of the presence of the nitrogen, it can undergo different reactions, right? That don't produce hydrogen gas, they produce other gases. And so, for example, nitric acid reacts readily with copper to form copper ions and other gases. That reactivity is beyond what we do in this course, but it's just a good idea to understand that nitric acid is a little bit different here. So at this point, we're going to understand how we utilize the activity series in order to predict these spontaneous reactions and whether they'll occur or not. Okay, so what I want to look at now is a couple examples and predict using the activity series whether these examples will be spontaneous or not. So our first example is zinc metal plus nickel ions goes to zinc ions plus nickel. So we're asking the question, will zinc be oxidized? Right? Zinc going to zinc 2 plus 2 electrons, while nickel, right, is reduced, right? Nickel 2 plus 2 electrons going to nickel metal. So we can use the activity series to show us this, because what we know is that in order for this reaction to occur as written, that the metal that we're oxidizing has to be higher in the table than the metal ions that we're reducing. So let's check out our activity series and see if this is true. So if we look at our activity series, we see that our zinc metal is here, right? So we want the zinc to be oxidized, and so we need to give it to ions below it. And we were looking at nickel ions. So yes, indeed, zinc is below nickel, so zinc will lose its electrons, give them to nickel ions to form nickel metal, and leave us with zinc ions. So that reaction would occur spontaneously as written. So yes, we could say that this reaction would occur. It would be spontaneous. Now, if we look at our second reaction, again, now we're looking at still zinc being oxidized. So we're looking at zinc going to zinc 2 plus 2 electrons. And we're looking at calcium undergoing reduction from calcium 2 plus 2 electrons goes to calcium metal. So again, we need to consult the activity series, and in order for this reaction to be spontaneous, zinc will have to be above calcium so that the electrons will flow, like this, right? So let's look back at our activity series. So if we look at the activity series here, again, we find our zinc right here. Now we're looking for calcium. Ooh, calcium is up here, right? So what we're asking is zinc to lose its electrons and give it to something up here, right? Something that wants to lose electrons more, right? So the idea is that this reaction, calcium wants to exist as calcium ions even more than zinc wants to exist. So to get the electrons from zinc to cause calcium to form the metal is not going to happen, right? So electrons will not flow up the table. So now so if we look back at our reaction here, we would have to say, as written, this reaction would not occur. So this would be no. It's not spontaneous. Now, of course, what would be spontaneous would be putting calcium metal with zinc ions to form calcium ions plus zinc metal. So this reaction would occur spontaneously, because if this direction is not spontaneously, right, what we're saying is that it would like to flow the opposite way, right? Calcium would like to give up its electrons more to the zinc ions to form zinc metal. So this is the idea. It's about using the activity series to predict whether a reaction will be spontaneous, whether certain combinations of metals and metal ions will actually react, as well as will metals dissolve in acid is another easy question that we can look at. So we're going to move on now, and we're going to talk about batteries in the next little episode here. So in this section, we're going to talk about batteries. So batteries are just electrochemical reactions that have been packaged, right? And so before we actually get into talk about batteries that we think about, we're going to talk about a more open style of battery, right? A battery that doesn't have fancy packaging. And we're going to use that to generate the ideas, and then we'll look at some of the commercial batteries that are available. So before we move into that, though, let's think about some common ideas that we think about with electricity. So we have the concept of current, right? Current is the flow of electrical charge. So when we talk about electricity, it's simply the flow of electrons through a wire, right? And so the current is the flow, right? The higher the current, the more flow, the faster the flow, if you will. Kind of like the river current, right? If a strong current means you have a stronger flow. So when we talk about electrocurrent, it's kind of the same idea. And since these redox reactions involve transfer of electrons from one element to another, they have the potential to create current. Now, this is not terribly easy to see when we look at examples that we've already seen where those electrons are just flowing over very tiny distances because everything is right next to each other in the same flask. But if we take those reactions that we've been looking at it and we separate the two processes, right? If we separate the oxidation and the reduction physically, but we keep them electrically connected, right? That's what we're going to look at now in what we call a voltaic cell. So a voltaic cell is a type of electrochemical cell that creates electrical current using spontaneous redox reactions, ones that we've been looking at, right? Ones that will occur just by combining the species together. Again, these are called voltaic or sometimes called galvanic cells. Now, when we set these up, there's going to be some vocabulary, right? We're going to have a metal strip on each part of the cell, right? We're going to have a metal strip where oxidation occurs. That's going to be called the anode, right? Two vowels go together, right? A and O, right? Anode and oxidation. And it's given the negative sign in our formalism. The metal strip where reduction occurs is called the cathode. Again, the two consonants stay together, C and R. Okay? So, reduction at the cathode, oxidation at the anode, and the cathode is given the positive sign in our convention. So, these two half cells, all right, we have the oxidation half cell and the reduction half cell, or the anode and the cathode half cell, are connected electrically, typically by attaching a wire from the anode to the cathode. Right? So we connect the two metal strips by a wire. Now, if we want to, along the way, right, we can have this wire run through a light bulb or some other electrical device or a meter, right, so that we can measure that flow of electrons, right? Or we can light a light bulb. We can use that electricity. those moving electrons that are going from one place to another, right? They're going to go from the oxidation, right, where they're lost, right? So electrons are lost here, and electrons are gained here, right? So electrons will always flow from the anode to the cathode, or from oxidation to reduction. Right? So it's always anode to the cathode, or from oxidation to reduction, or from the negative to the positive, right? Negative, thinking about the source of the negative charge maybe, would be a way to think about that, flows to the positive side. Now, there is one other part of a voltaic cell, and that's the salt bridge. And this connects the two solutions to one another, and it completes the circuit, or makes the circuit actually function efficiently, and it allows ions to flow between the two half cells. And this, quote, maintains electrical balance. Well, we'll just say it contains charge balance. It's probably easier to think about that way. Okay, so now that we have some of this vocabulary, let's look at voltaic cells. So this is a mock-up or a design of a basic voltaic cell. And so this is utilizing the reaction, one of the reactions that we've seen before, right? The zinc metal plus copper solutions goes to copper metal plus zinc ions, right? And we can see here are two half reactions, if you will, right? We have the oxidation half occurring here, and we have the reduction of the copper ions occurring here. So this is going to be our anode, right? So this strip of metal, what we call the electrode here, is going to be called our anode. It's going to be negatively charged, and we'll likely make it of zinc, right? Because that's the source of our electrons. It's what's being oxidized. So what happens at the anode side here is that the zinc of the electrode here, the zinc of our anode, loses the electrons and forms zinc ions that flow out into solution here. And the electrons leave the anode and flow through the wire, maybe through this light bulb, and they eventually reach the cathode. And at that point, they become in contact with copper ions in solution, and those electrons get transferred to the copper ions, reducing them to form copper metal, and that copper metal forms on top of the cathode. In this case, we made the cathode out of copper just for ease, but this could be made of some neutral substance or some substance that doesn't react, like graphite or maybe platinum or certain other metals. But typically, for ease of convenience, we just make it out of the same metal that we're creating. So some of the key things, right? We want to know the flow of electrons, right? Electrons will always flow from the anode to cathode. Now, by convention, we almost always put the anode on the left, the cathode on the right, so that electrons flow from left to right. Now, the one thing we haven't talked about is the salt bridge here. So the salt bridge, right, again, it contains an ionic compound, right? So it has ions that can flow into the solutions, right? Now, what ions are going to flow where? Well, if we think about what's happening at the anode, we're creating positive ions, right? So if we just let this go, we would overwhelm the positive. We would have too many positive ions here. We need negative ions to balance those out, right? So negative ions will flow toward the anode to balance out the positive ions that are created. So when I think about it as a circuit, right, the negative charge flows away, the negative charge flows back, right? And over here, we are depleting the positive charge, right? Positive charge is being taken away, and so we're going to get an excess of negative charge here. So positive ions have to flow into this solution again to replace the positive ions that were created. Right? So we think of negative charge flowing in, we have to also have positive charge flowing in to balance that out. It's another way to kind of imagine this. So there is our basic voltaic cell, or battery, right? So we talked about current, right? This is the flow of electrons. But the other big term that we usually use with electricity is voltage. So in a voltaic cell, there is voltage, right? Voltage is the driving force that causes the electron flow. It's what we call the electrical potential, right? And we have to have a difference in electrical potential between our two halves in order to get the electrons to flow. It's kind of like, gravity works, right? A river will flow downhill. Electricity will flow downhill, right? We need a difference in potential between the two halves so that the electrons can flow. Now, if we have a high voltage, that means we have a large driving force, right? There's a big difference between the potential, the electrical potential of the anode and the cathode side. Low voltage means there's a lower difference in electrical potential. And again, we use this analogy to water. So we have this difference in potential. We can think of it as difference in heights, if you will, if you want to kind of make it analogous to gravity. And the current is how many electrons are flowing, right? The higher the current, the more electrons are flowing. Right? So faster flow, higher electric current. Okay. So we have these two ideas. We have the flow of electrons, how fast, and we have this difference in potential that causes the flow. And we need there to be a difference in potential so that the electrons can flow from high potential to low potential, right? So we need our anode to have higher potential than our cathode side. So how can we connect this idea of the voltaic cell back to our activity series? Well, we can use the activity series, right, as a way to predict whether reactions will occur. So we can use it to pick out a pair of reactions that will occur, right, that will be a difference, right? So if we think of the activity series as a listing of potential, of electrical potential, where things that are high in the activity series have a high potential, things lower have a lower potential, right? We want something to flow from high to low, right? So we're going to want something high in the table to be oxidized, as we talked about, and we're going to want something lower in the table to be reduced. That creates that potential difference. So we want to pick a metal high in the table to undergo our oxidation at our anode, and we want to pick a metal that is lower, or a metal ion, and it will, that is lower in the table to undergo our reduction. This creates a potential difference and a voltage, right? And the bigger, the farther they are apart, the higher that voltage is going to be. Right? So you can make high voltage, low voltage, but the key is you need that difference. Now, if we combine one, if we put something at the anode that's below what's at the cathode, right, then it won't happen, right? We'll get a reaction that just sits there, right? No electricity will flow. Okay? So, example, you can't make an anode out of copper metal and a cathode containing lithium ions, right? It just won't happen. So it has to be a spontaneous reaction in order to use it in a voltaic cell. So again, we have our potential here. So if we look at our battery that we just created, right, our anode was zinc, right, and so in our cathode was copper down here, right? So we have a difference, right? We have a pretty good potential difference here. And so this will easily give up its electrons to the copper ions, or the zinc metal will serve as our anode, and the copper ions will serve as our cathode. Right? And so we got this setup. So when we think about voltaic cells, we have to have the oxidation that's occurring at the anode be higher than the reduction that's occurring at the cathode. Now, a voltaic cell will die, right? Like all batteries, they have a life, right? You can run them and eventually they become dead or depleted, right? In this case, right, when does that happen? Well, it happens when you run out of reactant, right? So eventually we will eat away at this zinc electrode and we'll get to the point where we don't have enough zinc here to really maintain any kind of reaction. And on the same sense here, we will run out of copper ions in solution eventually as they become converted into copper metal. So a voltaic cell, like any battery, will die over time. Right? It has a finite lifetime. In the next section here, I want to shift away from these voltaic cells to actual batteries, right? Which, again, are still voltaic cells, but voltaic cells that have been packaged in such a way so that they're convenient. So we're just going to go through and look at some survey of some different kinds of batteries. And what I want you to pay attention to is sort of the general construction, the voltage that they produce, and just facts. I don't expect you to memorize, chemical reactions, but you should be able to pick up sort of the basic ideas of what, the batteries, and then differences between the batteries. So the first battery I want to look at is what's called a dry cell battery. So this is the basic model behind our classic AA, AAA, C, and D type cells. Now, typically here the anode is zinc or sometimes magnesium. And in the battery construction, that zinc is located on the interior walls and on the flat bottom, right? And so my anode is located on the inside bottom and walls of my battery. So the outside, if you will, of the battery. The cathode is a rod, typically a carbon graphite rod, that has manganese oxide either built into the graphite or attached or plated or somehow mixed in here near our carbon rod. Right? And this gives us our cathode. We get the reduction of manganese here from what it is in manganese oxide to what it is in Mn2O3. Right? If we want to think about oxidation states, here the manganese is a plus. So here the manganese is a +4 here and a +3 here. So we're getting that reduction of the manganese. A dry cell battery produces a voltage of 1.5 volts. And it doesn't matter what the different battery is. The only difference between a AA, a AAA, and a C and a D is they're all 1.5 volts. It's just the bigger the battery, the longer it'll last. So a D cell will last longer than a AAA because there's more fuel, right? There's more reactants so that we can get more formation of product, right? More reaction. We can also connect these batteries in what's called series to produce higher voltages. So if you think about your calculator or other things that maybe take 2, 3, 4 batteries, right? It's because it needs a higher voltage, right? So if I put 4 batteries in there, I potentially get 6 volts out, right? We just add the voltage together. So that's your classic dry cell battery. Now, the one thing I didn't mention was the salt bridge, right? The salt bridge comes in the middle part, right? This ammonium chloride paste, right? This creates the ion exchange, right? It keeps ion balance. Now, the second kind of battery I want to talk about is what's called the lead acid battery. So you might recognize the picture here as the battery in your car, right? So lead acid battery is the prototypical car battery or motorcycle battery or boat battery, etc. Now, the lead acid cell is a 2-volt cell. So, but a typical car battery, for example, actually has 6 lead acid batteries or 6 lead cells in series. So it creates a 12-volt battery. So essentially, they've taken 6 batteries, packaged them together in series to make one big battery, if you will, that has a total voltage of 12 volts. Now, lead acid battery is kind of interesting because we have the same product formed at both the anode and the cathode, but they're coming from different sources. So at the anode, we have metallic or metal lead, right, which undergoes oxidation to lead plus 2. At the cathode, we have lead in the plus 4 oxidation state. Again, it's reduced to, again, lead sulfate in the plus 2. So all the lead ends up as lead sulfate, but it's coming from one source when it undergoes oxidation and another source when it undergoes reduction. Now, this is all in a bath of acid, right? Sulfuric acid. And this is where the lead acid comes from, and this is where the term battery acid comes from, is typically these car batteries which are bathing in sulfuric acid, right? This is what makes them sort of dangerous to mess around with, if you will, because this acid is quite dangerous if you're exposed to it or if you get it on your skin. And most of these batteries nowadays are sealed. You can't open them up to do anything with them. And so we can see here that, again, we have the anode terminal, the positive terminal of the cathode. They're attached to what would be the cathode shown here in red and the anode shown here in silver. Now, the other big thing about this battery is this battery is rechargeable, right? So when we drive, we're recharging our battery. So when we start our car, we get the discharge of the battery, right? These run in the directions that they're written here. On the recharge cycle, while we're driving the car, we're recharging this battery, allowing it to go back from the lead plus 2 back to the lead metal and the lead oxide, go back to its reactant forms. So this is one example of a rechargeable battery that we look at. Now, there are other kinds of batteries that we could talk about. I'm not going to go into detail, but you can think about some of the other types of rechargeable batteries that you may know, like nickel-cadmium batteries used to be a big thing, right, to use in cell phones or different things. Then there was nickel metal hydride batteries, which are still really commonly used in a lot of applications. And then the newest form of rechargeable batteries are lithium-ion batteries. And these are extremely common in things like cell phones and laptops because of their small size and lightweight. But we're going to shift from talking about those kinds of traditional batteries, right, to talking about maybe a less traditional battery, and that's called a fuel cell. So a fuel cell is still technically a battery. It is a spontaneous electrochemical reaction, but the key here is you supply the fuel. So where in a typical battery, right, they run until they run out, right? You deplete the supply. A fuel cell will never run out as long as you keep supplying the fuel. That's sort of the point, right? So they're batteries that don't ever go dead because you continuously replenish the fuel, right? The reactants. So the most classic form of this is the hydrogen-oxygen fuel cell, where hydrogen comes in at the anode, and undergoes an oxidation. And your products here are water, and this is in a bath that contains hydroxide ions, right? It's basic, right? And so the hydroxide ions react with the hydrogen gets oxidized to give us water. At the cathode, we have oxygen coming in. That oxygen reacts with the water, right? That's in this solution here, right? We have water, and that undergoes reduction and forms more hydroxide ions. So we replenish the hydroxide ions that are being used here. So they're used here and made here, if you will. And the only products, if we see here, are water and hydroxide ions, right? And the hydroxide ions are used, stay in solution and are used at the anode, and we form water, which could conceivably just continue to be used, or it could be, disposed of, if you will, or, used for some other purpose. But they're very clean, right, in terms of the products that are formed. So this is some of the advantages, right, of a fuel cell. They're very clean operating. You don't have to worry about metals like we do with batteries and maybe proper disposal of those, pollution, those kind of issues. Now, the drawback, of course, is you have to have a fuel supply, right? You have to continue to supply, especially the hydrogen. Oxygen can be gotten out of the air, but hydrogen needs to be supplied somehow, or whatever fuel source that we're using here. So hydrogen is the simplest. There's other fuel sources like alcohols and other materials that can function as the fuel at the anode. But again, you still have to have a supply of them. So portable applications of fuel cells can be a little bit troublesome, like in cars, because we have to store the fuel. Now, where fuel cells have been utilized a lot is places where we can have a dedicated fuel supply, stationary applications like buildings or spaceships, right, where there can be a supply of the fuel that we want there. So fuel cells, a slightly different version of a battery. Now, one place where fuel cells are very heavily used is in breathalyzers, right? So these breathalyzers that police officers carry around, these are functionally fuel cells, right? So basically the fuel, instead of hydrogen, is ethanol. And so when you breathe into one of these, any ethanol that's in your breath, right, acts as the fuel and is oxidized, and what you create is acetic acid and water. And the oxygen, right, which comes from the air, right, so it has an air intake, is reduced in the presence of water, again, to form the hydroxide ions. And so what it uses is, as this reaction takes place, right, it generates electricity, right? It generates an electric current. That current can then be measured by the device, and that measurement through some calculations can be converted into what they call the blood alcohol level. So it can convert the amount of alcohol in the breath. It creates a certain amount of signal. That signal, the amount of signal, is then correlated to some blood alcohol level. So the more ethanol you breathe in, right, the higher your blood alcohol level is going to register. So that's a functional, good example of where we use a fuel cell that maybe you didn't know about or hadn't thought about. So that kind of brings to a close what I want to talk about in today's class. Next time, we will look at some additional applications or some additional ideas involving electrochemistry as we wrap up Chapter 16.